Hello, sir. Srinu, sir.
Yeah, good morning, sir.
Sorry for the delay, sir.
Yeah, okay, sir.
So, all the participants, very warm morning to all. So, without any late, we will start today's session. Sir, over to you, sir. Srinivas, sir.
So, shall we begin, sir?
Yes, you can start, sir.
Okay, okay. Very good morning to all the participants. Welcome to the day 4 of the FTP. I hope you are having an interesting sessions all these 3 days. And I also hope that you are practicing some additional examples in your free time. Uh, So today we are going to see one application where we will be developing a Verilog code and try to deploy it in the on the hardware. As of now, we have designed combinational circuits like gates, and in a sequential circuit, we have seen counters, and also we got familiarized with the different types of flows, HDL to bitstream generation, as well as from block design to HDL generation, and from HDL to bitstream generation and deployment. So I think the prerequisites that we covered all these 3 days are sufficient, and now we can just go and have a hands-on on real-time designs and applications. So the as the title of our FTP goes as engineering signal processing and communication systems with FPGA. In today's example, what I'm trying to do is I will just give a problem statement related to digital signal processing. And with that problem statement, we will see how to develop a custom hardware architecture that addresses the given problem. If you remember, yesterday we had a brief discussion about FSMs, the two in particular algorithmic state machine with data part, that is ASMD. And yesterday I have mentioned that today we will be seeing the implementation of an FSM kind of architecture in FPGA. So now I will be taking one interesting signal processing problem, and then we will see how to design an architecture in order to address that signal processing problem. So let's begin without wasting any further time. Uh, so let me share my screen, my MS Word. Sir, kindly please confirm, are you able to see my screen, right? Hello? Okay, okay, fine. So the problem today that we are going to discuss is this is a very simple concept that I think everyone were aware of. So we are going to design a hardware architecture to compute uh, frame energy. To be precise, short time frame energy. So we have a digital signal. Uh, we have some samples like this. So what is the concept? Maybe we have an analog signal that we pass it to an ADC, analog to digital converter, and we get digital samples, right? So we have a signal, that is analog signal, that we pass it to an ADC, we get the digital samples. So in digital signal processing, there is one concept called signal energy. So the signal length will be of infinite in length, So computing the maybe if you take a speech signal processing, say for example, so how a speech signal is being processed. So once you get a digital samples of a speech signal, what we do is uh, we take only a block of samples. That block is called as a frame, and to that frame there is a one important parameter that is called as frame energy. So we will be going to compute generally for speech signals. When we get a continuous speech signal that is converted into digital format, we will get a continuous samples, discrete samples. So when we are getting a discrete samples, what we do in order to do speech signal processing, we do not take entire signal at a time. What we do is we take we segment that signal into a block of samples that we call it as frames, and we will process each and every frame. So while processing, there are many techniques which we follow in speech signal processing application. So one of the important parameter that we calculate from a speech frame is frame energy. So if you take any discrete signal, say that is x of m, where m is varying from 0 to some infinity. So in that case, how do you compute the energy? So in that case, the energy is computed as x of m modulus whole square summation m is equals to 0 to infinity. So this is the simple energy equation of a signal. So what is x of m? I told you earlier, right? We will be having discrete samples, and these samples are nothing but they have positive and negative samples. So we have two. So this is at 0 reference, and if you take any real-time system, it is a normal convention to limit the signal amplitudes to plus or minus 1 volt. So maybe minus 1 to plus 1. Either we take in this range or else 0 to 1 this range. There is a significance when it comes to digital hardware architecture. Why? Because if the data samples are in the range of minus 1 to plus 1 or else 0 to 1, if you do multiplication, the resultant value also lies within the same range. If it is minus 1 to 1, the resultant also lies in minus 1 to plus 1 range. If it is 0 to 1, the resultant also lies in 0 to 1 range. So generally in terms of hardware, only multipliers will consume relatively high amount of area or else resources on FPGA when you implement. So if your data is out of this range, out of minus 1 to plus 1 or 0 to 1, then whenever you are doing the multiplication, the resultant value is unbounded. Even you can just multiply and check. So there is no fixed boundary, so it is unbounded. It scales up, it increases. So again, in order to represent that number, the number of bits required also increases drastically. So as the number of bits increases, in order to hold them in a register, the size of the register also increases. So when it comes to hardware point of view, whatever the numerical operations that we do, we always take into consideration like it always falls within the range minus 1 to plus 1 or 0 to 1. Even in the case of speech signal processing, whatever the signal that we are taking, that also will be assumed like it is in the range of -1 to +1. So this is with respect to small basics regarding frame energy. So actually this is the equation that I have given is a signal energy. Here the signal is of finite length. So and we are calculating the energy of a speech frame having some finite number of samples. That's why it is called as frame energy. And since I told this is a finite length, if you see this in the perspective of a time duration, the time duration generally varies in between 10 milliseconds to 30 milliseconds. So that's why it is a very short time. So hence theoretically it is called as short time frame energy. So this one for the sake of simplicity throughout this FTP, what I will refer it as, I will just refer it as frame energy. So frame means a finite number of samples. Say for example, either 128 samples or 256 samples or 64 samples. So some finite in number. So what I am asking is, if I give the define the frame size, and if I give you the signal samples, and I am asking you to calculate the energy. So this is the overall problem statement. So for this we need to design a hardware architecture. So we will see how to do that. But before proceeding to that, we need to have some prerequisites. So the first one is mm, uh, what is a data format? So each speech sample or each frame sample, what I'm doing is I'm giving you the specifications, because with these specifications only ultimately we have to design the hardware architecture. So all the frame samples are of 16 bits, and these samples are represented in signed fixed point format. I will tell you what is signed fixed point format. So as of now, each signal sample is represented in 16 bits, and what is the data range? Data range varies from -1 to +1, and I'm telling it as each sample is represented with a signed fixed point data. So in the signed fixed point data, we have integer part and fraction part. So actually, what are the data formats? There are two data formats. One is fixed point data format. Other one is the floating point data format. So again, in floating point, we have 32-bit floating point and 64-bit floating point. And 32-bit, we call it as single precision floating point, and 64-bit we call it as double precision floating point. So this floating point either 32-bit or 64-bit in length. This is as per the convention, single precision or double precision. This is follows the standard of IEEE. There's one standard is there. I just forgot the number. 1 minute. $754. Yeah. IEEE 754. This is a standard that is defined by the IEEE regarding the floating point architecture. So all our modern computer systems, we just say like it is a 64-bit processor, right? So it has a capability of handling 64-bit floating point values. So if you take the structure of a floating point number, so if it is a 32-bit or if it is a 64-bit, it has a fixed definite structure. So you can just go through some basics over here. So if you take a 32-bit floating point, we have one sign bit followed by 8 exponent bits followed by 23 mantissa bits. So similarly, we'll have a definite structure for 64-bit as well. So how the numbers, any number, how it is represented in this exponent and mantissa or 32-bit floating point or a 64-bit floating point, that you can just go through this standard and you can refer it. Since we are not dealing with floating points as of now, it is out of the scope of our FTP. So I just gave you a brief overview details. You can just go through how a floating point format looks like and how a number is represented in floating point representation. So that you will just refer it as like a homework kind of thing. But when designing custom hardware architectures, you have to decide whether to choose a fixed point or a floating point. So obviously floating point will have a high precision value. Why? Because you are representing a data sample with a minimum of 32 bits in a single precision or a minimum of 64 bits in case of double precision. So the precision is very high. That is the advantage of floating point. But at the end, what is the disadvantage is, since you are dealing with a very big numbers, each number is represented with either 32 or 64 bit. The corresponding data manipulation hardware, maybe if you take a adder or a subtractor or else even a multiplier, since the operations are being performed on very big data sequence having a more number of bits, and also it has a specific frame format, right? Exponent and mantissa, you need to do some kind of an operation with respect to exponent and mantissa along with the sign bit in order to get the exact value, what the exact value that is being represented. So if you take all these factors, so the corresponding hardware architecture will be pretty complex and it will be huge. Even if you implement on FPGA, it will utilize more number of resources. And if you put it on a silicon, in case of an IC fabrication, the components will occupy a pretty much large area. So there is often a trade-off. So if you don't require such a high precision, even with a reduced precision, your application may still work. Then it is not an always a best choice to go with the floating point numbers. So generally, what the designers will do, they will go with the fixed point notation. So coming to what is a fixed point, as the name suggests, the point is fixed by the end user. So there is no specific format, like there is no constraint like you need to take these many number of fixed bits like that. So the choice is ultimately at the end user. So Only thing is that in the floating point, the point is fixed. Sorry, in the floating point, the position of the decimal point is by default fixed. So there is no, the point will not move anywhere else. So all the operations can be computed without any difficulty. But in case of fixed point, as the name suggests, the point position of the decimal point is fixed by the user. So depending upon the representation of the numbers, the fixation of the decimal point will keep on varying. So whenever you are performing any arithmetic and all, uh, you need to always know where the point is, and accordingly you need to develop your architectures. So I don't want to confuse you further. While we are implementing the designs, then you will be come to know what it actually looks like. So coming to the fixed point, so if you take any number, real number or anything, say for example 1.2345, so this is called a fractional part and this is called as an integer part, right? So any number, so this number can be represented in by infinite number of bits. In floating point we may represent with 32 or 64 bits, but in fixed point uh, has the user can make a decision like with how many bits he would like to represent. So as say in our example, what I'm telling is I am representing all samples with 16 bits and the data range is from -1 to +1. So data will be positive and negative. So in order to identify whether the data is a positive sample or a negative sample, I definitely require one sign bit. So one bit I reserved for sign bit. And if you see the integer part, it is always the 1. So maximum value in both the directions is 1. So beyond 1 we don't have anything. And in order to represent a numeric decimal value 1, we require 1 bit. So in my integer part, I am using 2 bits. So out of 16 bits, 2 bits I'm reserving for integer part, and remaining 14 bits, what I am doing is I am using it for to represent the fractional part. So this is how my data format is. So why, since I told like it is a 16-bit data that is represented in signed fixed point format. What is the format I'm using? 2.14. So 2 bits for integer part, 14 bits for fractional part. So this I have illustrated for your understanding, but in actual notation we will use signed fixed point 2.16. 16 is the word size and 2 is the integer size, integer part size. Now from this notation the fractional part size can be given as word size minus integer part size. So that is 16 minus 2, which is equals to 14. This is a standard representation. We will represent the word size followed by the integer part size. From this we will derive the fractional part size. But for your understanding, throughout this FTP, I will represent it as 2.14. So 14 for fractional bits, 2 for integer bits. So 2 plus 14 is equals to 16. It's not like this is wrong, but for your understanding, since you're at a beginner level, I don't want to confuse with this type of notations. I will just use this notation 2.14. So 14 plus 2 equal to 16. 2 for integer part, 14 for the fractional part. So this is about the data format. And the next thing, that is I want to explain is next, what is the frame size that you need to take? Typically, if you take since we are talking about speech signal processing, the frame size generally varies from 8 to 1024. So while designing our hardware architecture, our main motivation is this frame size we will make it as a variable, and the user should be able to provide his desired frame size to the architecture. And once a frame size is given, say for example maybe frame size is 10, then it should able to read 10 data samples and then calculate the corresponding energy. So how it will calculate? Energy is equals to summation m is equals to 0 to 9 modulus of x of m whole square. So since the frame size is 10, so that is 0 to 9 x of m whole square. Actually, it is as per mathematical formula, it is m equal to 0 to infinity. So this infinity is of finite length that is given by the user. So once a value is given in our hardware module, it has to calculate the energy on the streaming samples. So since this is a signal, the samples will come with a particular time period like this to the input module. So if we give frame size 10, so it has to collect the first 10 samples and then calculate energy, and the streaming happens continuously. For the next set of 10 samples, it has to compute another energy value. For the next set of 10 samples, it has to calculate another energy value. So this process keeps on continuing until the until we get the signal. So I think this much theory is sufficient for us as of now in order to proceed. So how our actual module looks like. So a rough diagram. So we are going to design a black box, that is to compute frame energy. So obviously this module should have a clock signal. Since it has some sequential component, we need to drive with a clock signal, and it should also have reset signal. Why? Because we need to reset the internal registers, and we have to give a control signal called start. So when we are telling this, when we are giving this start signal, then the frame energy module, this is a module, hardware module. When you're providing the start signal, then the module will understand like, okay, signal is coming to the module, now I need to calculate the energy. So that is indicated by the start signal. If start is 0, then no signal is coming, then the module will be in the idle state. So it will wait for the speed signal samples to arrive in order to calculate the energy. So once we give a start, then the frames energy module will go into the computation phase. It will jump from idle state to computation phase, and it will wait for the speech signal samples to arrive. Whenever the sample is coming, it has to take that sample and compute the energy value. So the start is like a control signal. And once the start is given, the frame energy module will look for the speech frame samples, right? So we have an input called frame sample. So on this input, we will stream our signal samples. But how our frame energy module will know a valid sample has arrived or not? So it should not read the data bus continuously all the time. Only it should read when an appropriate sample arrives on this input. how this module will know a valid and appropriate sample has errored with respect to another status signal, that is frame sample valid. Whenever this valid signal goes high for at least one clock cycle, then we assume that a valid sample has arrived on this bus. Then the frames energy module, what it will do, it will read the frame sample bus, it will take the data in order to compute the energy. So to this module again, we also has to define what is our frame size. So how many samples it needs to do the summation. We know, right, what frame energy equation, that is summation m equal to 0 to infinity x of m mod whole square. So what is this infinity value? So how many samples it needs to square and appropriately do the summation to calculate energy. So that is called frame energy size, frame size, that we are going to give as one more input. So with all these inputs, what the frame energy module will do, it will calculate frame energy. And how we will know whether the data on this frame energy, whatever the data is coming on this frame energy, it is a valid frame energy value that is computed by our frame energy module. So for that, what we'll do, we will valid frame use one additional output that is called frame energy valid signal. So whenever this valid signal goes high for at least one clock cycle, then we assume that whatever the data that is coming on the frame energy bus, then that data is a valid frame energy value computed by our frame energy module. So in this way we just assume that, and we will use one ready signal. This ready signal is nothing but to indicate the operating status of our frame energy module. If our frame energy module is in the idle state, the ready is will be high, indicating that it is idle, and subsequent stage can give the speed signal or the signal samples to our module in order to calculate the frame energy. While it is calculating the frame energy, what it has to do, the ready should be active low, indicating that it is it is busy and it is in the computation phase. So in order to denote this operating status of the frame energy, we will use one status signal. So that's it. This is a module, high level architecture that we are going to design in our today's session. Up till here, if anyone has any doubts that I can clarify, or else I will be proceeding with the further discussion. So I guess there are no doubts, so I will proceed.
You can proceed.
Okay. So I will just give you one example about the signed fixed point representation. So I just opened the MATLAB. So I will be taking a small example like 2. Sorry, taken between 1.09764. maybe something like this. Now what I do is we'll try to convert into signed fixed point. There is a inbuilt function in MATLAB to convert any numerical value in signed fixed point representation. So signed fixed some data. Yes. Volume is 6. And so this is a signed fixed point representation of a number 1.2369. Say for example, for your understanding, let me go to one website. Decimal binary converter. So what is the value I have taken? 1.2369, right? So 1.2. If I convert it into binary, you see this value is represented with one integer bit. Why? Because the integer part is 1. In order to decimal 1, in order to represent decimal 1 in binary, we require 1 bit in binary. So 1, and you have a fractional part, that is 2369. In order to represent 2369, there are infinity number of bits required. So in this, what I'm trying to do is I'm only taking in from the integer part only 14 bits. So 1 2 3 4 5 6 9 10 11 12 13 14. If you represent it with only 14 bits, you will see what is the resultant value. So it is 1.2368 77744140625. So whenever you are representing with a shorter number of bits, so that means you are truncating, obviously your precision will reduce. So our actual number that we have taken earlier is 1.2369. In order to represent this in binary, we have a infinity number of bits. You can see here, so it is continuing dot 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 infinity number of bits. So from this, if you take only the, since we are now dealing with only fixed point notation, we are only taking a fragment, a small portion of it. In the fixed point, we reserved 14 bits for fractional part, 2 bits for the integer part. In the 2 bits, 1 bit is the sign bit. Since here the sign is positive, the sign bit is 0. That's why we couldn't say anything. And remaining 14 bits, if you just copy from the top, and then that binary fixed point representation, if you convert it into decimal format, we got the equivalent decimal value. So that is 1.2368 77744140625. That is far less when compared to the actual value. So what is the error in the representation? So this value minus original value 1.2369. So the error is in the order of 10 power minus 5. So this is how the fixed point representation looks like. So this is one of the example that I just wanted to show how the fixed point notation is generally used. Say for example, if you take this again, all this infinity number of bits, and if you try to convert into binary, sorry, if you try to convert into decimal, even if you take all this infinity number of bits, you still won't be able to reach to your actual representation. So actual value is 1.2369, but you end up in 1.2368, 9999999, so on and so forth. So you actually, in order to represent this number exactly, we need infinity number of bits at the fractional part. So there is a other way of dealing with all these numbers in floating point representation. So there we have a concept of called as exponent and mantissa. That is slightly different type of a notation that you can just go through it at a later stage. So this is a quick note on fixed point notation. So now without wasting any further time, we will directly jump into the design of our model. Yeah, excuse me, I'm receiving an echo. Please mute all the mics, please. I think Suresh A. You can please mute the mic. Yeah, thank you very much, sir. So now I request you all to open Xilinx Vivado. Now we will start the HDL description coding for our frame energy module by using the concept of ASMD, algorithmic state machine with data part. And sorry, I forgot to explain one more concept. So this what we are trying to do, we are trying to model it by using the concept of ASMD. So it's a kind of a state machine. So for the sake of simplicity, we are considering only two states, that is S0 and S1. So whenever you are switching on the power of our frame energy module, when the power is on, it jumps into the S0 state. And whenever the start is low, that means you are not getting any start signal. That means when start is low, there is no speed signal to calculate energy. So in that case, what our module will do, it will remain in the S0 state. So this is like this. So whenever a signal is going to arrive at the module, start will be like active high. Then what our module will do, it will jump from the ideal state to the computation state. So S0 state, we call it as ideal state. And S1 state, we call it as a computation state. Where in this computation state, it will try to compute the frame energy. So whenever start is coming, it jumps to the S1 state. So when start is equals to 1, it jumps to the S1 state. So in this S1 state, what it will do, it will keep on scanning the frame sample output and frame sample valid. Whenever a frame sample valid will come, it will read the data on the frame sample bus, and it will, what it will do, it has to do two operations. First thing is, it has to square the obtained sample. That means it has to multiply x of m into x of m. That means it has to square. This operation it has to do. And there is one register called energy register. Maybe you can treat it as an accumulator. This squared value, it needs to add it to the accumulator. So the squared value, we call it as P, that is product. The product is always added to the accumulator register. That is E is equals to previously stored energy value summation value plus P. Why? Because we need to calculate the running sum, right? Running sum of the squares of the samples. So when a first sample is coming, already by default the register is 0. initially. So first product value will goes to register A. When second sample is coming, that square we will do it. That squared value should be added to the already existing resultant, partial resultant, which is so like that. The ASMD or the FSM needs to stay in the S1 state until all the samples of a particular given frame size has been processed and energy for that frame has been computed. Say for example, we say we have a frame size of 10. So after computing the energy by using 10 frame samples, then only the FSM should switch from S0 state to S1 state to S0 state. In all other cases, it has to remain in the S1 state in order to do the computation. So when all the samples for one particular frame duration has been processed, then what it has to do? It has to return to the idle state. So this is the scenario that we are going to address. So our ASMD is going to have two states. One is the idle state and other one is the computation state. And accordingly, what we'll do, we will write the description for the S0 state and write the description for the S1 state. So for this purpose, what I do is I just asked you to open the Vivado. You create a new project. Maybe you can create under the FDP folder, you can create a day 4. In the day 4, you can create maybe lab 1 folder. Click on next and then just save it. I had already created my file, so I will open my project. So somewhere as you desire, you just create a directory, maybe day 4 and then lab 1. Once the directory is ready, then what you do, go to add sources, create design sources and name the file source file as frame energy. On the screen you can see the frame energy. I will increase the font size just a minute. In the meantime, you please create it. Just create a model frame image. So I will do coding once again for you, though I have already the existing code. And open that file, blank file. You can open in Vivado, but anyhow, I have already created a project. I will do one more time the coding for you people. So for that, I'm just opening the text file. So as a keyword called module. So I think everyone has, I assume like everyone has created their empty module file. Do you want me to wait or shall I proceed? Please acknowledge me. Hello.
Okay, sir. Proceed, sir.
Okay, okay. So everyone has completed up to this stage, right? Uh, So
Yes, sir.
we have a keyword called module and our module name is frame energy, and we have a parenthesis ended with a semicolon. So this is a syntax, right? So to define the port list. So how it goes. So in the diagram you can see here in our actual, this is a module which we are interested to develop, right? So it has a clock, reset and start. So just and those inputs, input, clock, next input, start, next we have to do the frame size input, right? So as per I mentioned you earlier, the frame size, as per our specifications, we need to address in between the range 8 to 1024. So the maximum frame size that is allowed is 1024. To represent 1024, we require 11 bits. Actually, if you use 10 bits, we can represent between 0 to 1023, but you cannot represent 1024. In order to represent 1024, you require in binary total 11 bits. So our frame size input will be like in 11 bits, right? So input 10 down to 0. So next, from the diagram you can see we have frame sample. So as per the notation, I told like it is 16 bits and the format is signed fixed point 2.14, 2 bits per integer part, 14 bits per fractional part. So this 2.14 is only should be in our mind. In hardware we cannot place any decimal point in hardware. The 2.14 is our notation, that is virtually it should be in our mind, but not in hardware. In hardware we have to tell only in the terms of total number of bits, that is the bus width. So the bus size is 16 bits and in input name is frame sample, right? So it is down to 0, that is 16. Next, from the diagram you can see when how our module will know whether a valid frame sample has come. We need to acknowledge on a status signal, that is frame sample valid. This is only a 1 bit input. So after that, now we are dealing with the outputs. So the first output is frame energy. So frame energy is again a bus. We have to define what is the frame energy. So for this, how to define the buzzword, it is very important. Now you have to just pay attention clearly. So what is our frame size? Max frame size that I have considered in our design. So the maximum frame size that we have considered is 1024. And I told you What is the data range? It is -1 to +1. And you know that energy is nothing but summation of m equal to 0 to infinity x of m whole square. Now say for example our frame size is 1024, and what is the maximum value that a frame sample can have? Maximum value is 1, right? Since the data range is -1 to 1, the maximum value that a frame sample can have is 1. Now if you assume that all these 1024 samples in a one particular frame are 1, then what is the energy value is? Again it is equal to 1024. Why? Because square of 1 is 1, and running sum of all ones for a frame size of 1024 is nothing but energy value is 1024. That means maximum energy that you can calculate from a frame is 1024. Am I correct? So you don't have any doubt regarding this, right? So why I'm calculating the possible, what this is the maximum possible energy for the maximum frame size. But this condition will not come this very frequently. Why? Because this is very rare, very rare. But while designing a hardware architecture, we need to take into consideration what are the all possible constraints, and accordingly we need to define the size of our registers, or else the size of the output buses, so on and so forth. So the maximum energy is 1024. So to represent 1024, we require 11 bits. Now you see each speech sample is represented in 16 bits, right? It is having 2 integer bits and 14 fractional bits. In these 2 integer bits, one is the sign bit, other one is the magnitude bit. The magnitude value may be either 0 or 1. Why? Because the data always lies between -1 to +1. So maximum value is 1. To represent 1, we require only 1 bit. So this is clear, right? And you can see we have 14 fractional bits. So ultimately when you are doing energy is equals to summation of x square, right? So whenever you are squaring it, in the first scenario what we considered, all values are 1.0, 1.0, 1.0, 1.0 up to the maximum frame size. That's why we got 1024.0. So with this, what we told, like in integer part, to represent this maximum energy we require 11 bits. So that is okay, fine. Now all values are not integers, right? But in all, maybe in another scenario, if you take the samples may be 0 0.1, 0 0.5, -1.0, -0.25, so on and so forth. So it will be like real numbers with having decimals. So again when you square all these samples, again the energy value maybe will come like some integer part followed by fractional part. And this fractional part, how many bits we are taking from our actual representation? 14 bits. So since our signal sample has 2.14 format, we are having 14 fractional bits. Even if you calculate the energy, the resultant energy also will have 14 fractional bits. So that's why it also requires 14 fractional bits. So earlier if we take in this scenario we took like all samples are 1 means maximum frame size is 1024. This is like integer part. If we want to represent that integer part, we require 11 bits. So 11 bits is the maximum integer part and 14 bits is the fractional part. And as you can see here, energy formula is E is equals to modulus of x of m whole square summation. Though x of m is plus or minus, it is positive as well as negative. Since because we told like the range is from -1 to 1. Whenever you are squaring, all the subsequent coefficient resultant value will always be positive and energy value is also positive. There is no scope that energy value is negative. So in this case we don't require a sign bit. So without a sign bit we can still work. So what we call this format as unsigned fixed point format, unsigned UFX fixed point format. Now to represent that our final ultimate energy value, so how many bits we require? 11 bits in fractional part and 14 bits in 11 bits in the integer part and 14 bits in the fractional part. So how much it is coming? Total 25 bits, right? So 11 plus 14, so total 25 bits are required to represent the energy value. So in this way we have to calculate the bus widths, the limits of the bus widths. So from this our analysis we came to a conclusion that if a frame size for a maximum frame sizes of 1024, for a maximum frame size of 1024 samples, the energy value, in order to represent the energy value, we require 11 integer bits and 14 fractional bits, so total 25 bits. So the total 25 bits are required, so that we represent as 24 into 0. So that is frame energy. Next, how we know that the energy value computed by our module is a valid energy value or not? So for that we are using frame energy valid signal. So for that what we have to do? Output next. What is the other output? Finally we are left with one output, that is called as ready. So purpose, what is the purpose? To indicate the status of our module, whether it is idle or whether it is busy in computing the energy of our signal frame or speech frame. So this completes the port list description. So we have defined the port list successfully. I hope till here everything is clear. If anyone has any doubts, you can please ask, or else I will proceed with further description. Any doubts?
No, sir.
Okay, then I will proceed further. I hope everyone has completed up to this step. So everyone are ready, right? So now what we will do is, yesterday if you remember, I told like I will be discussing about one of the template for designing the FSMs, or else maybe the algorithmic state machine with data part. So now I will discuss about that template. So before that, let me open the generalized block diagram. So if you remember yesterday we were discussing about this diagram, right? So a typical ASMD or an any FSM, it has an integrated control part logic and data part logic. In both control part logic and data part logic, we have sequential state register logic, combinational next state logic, and output logic. And also each FSM or an ASMD has some finite states, and in each state we will do some particular operation. So for this purpose, coming to the template, so first you have to declare the number of states that you are using in the ASMD. Technically we call it as state encoding. So what is state encoding means? You can see here we have three states. I think in this diagram we have four states, right? Each state is given with a binary sequence or a binary value. Each state is represented with a unique binary value. Each state is represented with a unique binary value. That we call it as state encoding. So in our frame energy, I told you like we will use a two-state ASM in order to model our circuit. So how to do state encoding in this case? So in order to do a state encoding, there is a keyword called local param, PARAM. It's like a local parameter that is local to this module, that is frame energy. So we are considering state S0, so that we are parameterizing. So means we are creating a parameter called S0 for our reference. So what is S0? It is a S0 state, and S1 means S1 state. So this is our ASM state machine having two states, that is S0 and S1. S0 and S1 is for our reference, but in hardware we need to represent it with respect to a binary code for each and every state. So for that purpose, what I'm doing, S0 state I'm representing with a binary 0, that is 1 tick B0, and local param. I have taken S0, S1 for my reference. If you want, you can give any generic name, state 0, state 1, as you wish. Keep it simple, I have taken S0 and S1. If you are having four states means you require at least 2 bits to represent four states. If you have more than four states, that means maybe up to 8 states, you require 3 bits to represent each state. So that you know, right? So since I'm having only 2 states, I'm representing with 1 bit. 0 means bit 0 means state 0, bit 1 means state 1. Now, as you can see in the diagram, I told you, right? In the diagram you can see here, right? We have sequential state register logic. As the name suggests, sequential, so it is dependent with clock. State register, so register means just like a register to hold which stores the data on arrival of a clock edge and outputs the data. So we need to declare few registers in our design, and combinational next state logic is there, right? That is driving the sequential state register. So this we call it as elements, because this is a, as the name suggests, combinational. So it is a combinational logic that is driving the registers. So combinational logic, irrespective of the clock, it will calculate the value by taking the external inputs or an internal inputs or the input that is fed back from the registers, and depending upon some condition it will calculate some output and it will drive the register. So, and a register will be updated with the driven value on arrival of a clock edge. So these are the combinational logic elements. So what I'm doing is, so we have seen like for each and every register, just a minute, yeah, you can see here, this is a general representation. For each and every register there is an equivalent combinational next state logic that drives the sequential state register logic, correct? So as per the template, now what you have to define is registers and next state logic element so you have to declare any registers or next state logic or elements that you are going to use. After that, what you have to do is, I'm just giving you the details of the template. So in the diagram you can see, now we have to write descriptions for the sequential state register logic. When I'm referring to sequential state register or combinational next state or output logic, I'm referring both for both control as well as data part. In ASMD, control and data both are integrated. So this is a diagram, this is the control part and this is the data part, but these two are integrated together. It is not separable, but for the way of illustration here we have shown two separate entities, but actually these are integrated. So now what I do is, we need to write the description for the sequential state register logic, combinational next state logic and the output logic. So how we will write is, register logic description we have to write. Next, combinational next state logic we have to define. So coming to the sequential state register logic, and one more thing that you need to keep in mind, I have mentioned you like the levels of abstraction, right? So in case of ASMD or an FSM, we are using behavioral level of abstraction along with data flow. We are not using any structural. This is the highly preferred one, behavioral and data flow. So coming to the sequential state register logic, this sequential state register logic, whatever we are discussing, this we have to write it in behavioral. Combinational next state also we have to write it in behavioral. only the output logic will be in the data flow. Now that we will see how it will be. So when we are describing the sequential state register logic in behavioral, I mentioned you earlier, behavioral means you have to use only procedural statements. If you want to use only procedural statements, you have to define all the procedural statements within a block, and that block is called as always block. So I will write always block. Always at the rate, you have to give sensitivity list, begin and end. Since we are dealing with the sequential logic, we have discussed earlier, for the sequential logic, mostly the sensitivity list will carry the clock and reset signals. So we want our circuit to operate at passage of the clock. So passage of the clock. We are, if you want asynchronous reset, you can give passage of reset. Otherwise, if you want synchronous reset, don't include the reset in the sensitive statement. You have to include it in both. So we are doing a synchronous reset. So for that, what we are doing, we are not including the resets. So this is a syntax. And so sequential state register, sequential circuits, always in the sensitivity list, we will write clock, begin and end. Now coming to the combinational logic, again we are modeling it using behavioral logic. Again in behavioral, we have to use only procedural statements. If you want to use procedural statements, you have to use always block. So again, always and I told you a blind thumb rule. In case of a combinational logic, you keep the sensitivity list to be star mark. Star means it will be sensitive to all the signals, not with respect to a specific signal. So combinational, we will generally use this star notation. So always at the rate star. You can also keep parenthesis star, that was also allowed, or else this is also allowed. So in this case, we have to do it. Next, coming to the sequential logic, the sequential logic is sensitive with respect to a clock. So that's why we have written always at passage of the clock, begin and end. So whenever clock is coming, what it has to do, that you have to define at the begin and end. Here there are two things. Whenever a clock is coming, then it has to do a certain task. That task is again dependent on the reset signal. When reset is coming, it should not do any task. If reset is not coming, it has to do the task. So for that purpose, what we have to write, if it is coming, what it needs to do, begin, else if no reset is coming, what it has to do, begin and so this is the case. But for time being, what we do is we will take active low reset. That's why I will keep as tilde. Why? Because earlier yesterday I told you, right, whenever you are doing block design, it is always preferable to use active low reset. Why? Because whenever you are using a clocking wizard IP core, the locked output of the clocking wizard IP core can be directly used as a reset signal. So in order to make use of that one, I just made it be active low. Or else if you want, you can make it active high also. That is not a problem. So up till here, it is okay. Now what we have to do, carefully observe this diagram. I will open once again. So if you carefully see the output logic, it is always driven by the sequential state register logic. So whatever the value that is being stored in the register, that is going to the output logic, and that value is going to the output, actual output of the module. So again, here also the sequential state register logic, the value stored in the register is driven to the output logic, and this value is going to the output of the module. So if you take our module, we have three outputs. So frame energy valid, and ready. Now we need to drive all these outputs via a register as per this convention. Which convention? See, the outputs, the main outputs of the module, whatever we are having here, outputs are driven, we are getting by the output logic, that is okay, fine. But how this output logic is coming? It is driven by the sequential state register logic. So now what we have to do is, we need to create registers for each and every output, and from that register we have to drive these outputs. So for that purpose, what I am doing is, first we will create register for frame energy. So register 24 down to 0. Actually this is reg, this is not a pure register. When it will become a register, I will let you know. Reg 24 down to 0. For the sake of convenience, I will use the same names. Frame energy underscore reg, that means it is a register. And you can see from the diagram, right? Again, the sequential state register logic is driven by the combinational next state logic. So for each and every register, whatever you are defining, you have to define an equivalent driving force by the combinational next state logic. So for that, what I do, the combinational next state logic, I will give name as frame energy underscore next. Why I give next? Why? Because this combination next state logic will calculate the next value priorly, and this next value will update in the register on arrival of a next clock edge. So when next clock edge comes, this next will go inside the register, and immediately this value is fed back, right? Either it may be fed back, or it may take a new inputs or any external inputs or something, and it will pre-calculate the further next output immediately, irrespective of the clock. But when the clock comes, that next value goes into the register. So for each and every register what you are defining, you have to define a counterpart of the combinational next state logic. So in order to drive this frame energy, I need a register. That's why I'm declaring a frame energy register. And this register should be driven by the combinational part, right? Combinational logic. For that part, I'm defining as frame and energy underscore next. So this is the notation. Now from this register, I need to drive this output. So for that, I told I will be using data flow modeling. So where I have to go? I have to go to the output logic. In the data flow, we will be using assign statements, right? Assign is a non-procedural statement. We are assigning this output, that is frame energy. With what we are driving that energy, we are driving that output via the register, that is frame energy underscore register. Correct? So actually, how this frame energy reg is actually a reg type. How it become a register means, we need to add it in the sequential state register logic. Then only it will become a register. That means we have to make this reg data type sensitive to clock. So for that, what we are doing, whenever if reset is coming, what we need to do, that a frame energy range needs to be reset to 0, that is 25 tick D0. If no reset is coming, what it needs to do, this register needs to follow the output of the combinational next state logic. Correct? This register needs to take the value from its combinational next state logic on arrival of a clock signal. So it's the same thing that we are writing here, that the register same energy image given by combinational counterpart. And in the combinational next state logic, suppose, say for example, maybe in this combinational next state logic, I told right you will be writing some operations in order to update the sequential state register logic. So by default, if you are not performing any operation, whatever the value in the SSRL, that will go to C combination next state logic. When you are not performing any operation, that same value should go into the register. So it should be in the form of a loop. When you are not operating on anything, when any condition becomes valid and when you are operating, then the combinational next state logic will do some data manipulation and that new data will go into the register on arrival of a clock. So for that purpose, when nothing is going to happen, then what it has to do, combinational next state logic should follow the register. So understand clearly. So when positive clock edge is coming and if reset is applied, then register should be reset to 0. When no reset is applied and clock edge is coming, then register should follow the combinational next state logic. So combinational next state logic value should come into the register. Okay. And while defining the combinational next state logic, whenever you are not performing any operation, then combinational next state logic should directly follow the register. Otherwise, it has to, whenever a particular condition has happened, then it has to modify this value. So how this will modify the value, that we have to define the conditions that we will see later, but this is a default condition. Whenever it is not operating or manipulating anything, then it has to follow the register value. And so the same register value, what we have done, we have driven it to the output. In this similar way, what we have to do, we have to define a register for frame energy value. So and this frame energy value register, by default it should be reset to 0. So even in the absence of the frame, it should not tell, even in the absence of energy value, it should not tell energy is valid, right? So when you reset, everything will be 0 and the energy value on the frame energy output, that is also should be it is not an actual energy value. That's why by default the valid signal will be at a 1 tick DC. And whenever there is no reset signal, what it will do, it will On arrival of a clock edge, it will follow the next state value. Again, when you're not manipulating it anything, the next state value will be the value same as the one which is already stored in the register. This will be a little bit confusing, I can understand, but this will be clear when we write some certain conditions that I will let you know, but as of now, you just remember like this. Next, finally, what we are doing, what we have to do, we have to drive this output via the output logic, right? So for that, our output is frame energy valid, right? So we are writing assign frame energy valid. We are driving it via a register, that is frame energy valid underscore reg. I can see that some people are waiting in the lobby. So host, please check. I think someone is waiting. Please allow them.
So there is some technical glitch. It's not getting accepted. Now it starts.
Okay, fine. Thank you for your. So similarly, one more output is there, that is ready. So for that, again, we will create one register that is ready underscore reg, and a next state value that is ready underscore next. Now, when you are applying a reset, ideally the module will be in the idle state. Idle state means it is not doing any work. So the ready should be one tick B1. When reset is not there, then sorry, this is not ready. It's ready underscore reg, because in this sensitivity list we are. So when reset is not there, what it will do, the sequential state register logic will always follow the combinational next state logic. So ready reg should be equal to ready next. Next, in the ideal case, when you are not doing anything, the combinational next state logic should follow the sequential state register logic when you are not manipulating anything. So then ready underscore next underscore next. And one thing you can notice here, in the sequential logic, everything is sensitive to clock, right? That's why I used non-blocking statements, that is less than or equal to. This in the makes sense, right? So when the positive clock edge comes, all the right hand side will be evaluated at first, and at a time on the clock edge, all these registers will be updated in parallel, not in sequential. But in case of combinational next state project, I used blocking statements. So first this will be done, next it will goes to this operation, next it will goes to this operation. So that is the case. Next state logic, we have declared output logic. True output logic we have connected to the module outputs. So our code is okay, fine. And now I told you earlier, what means now when power is switched on, our ASMD switches to the S0 state. When start signal is coming, it will switch to S1 state. So how do you know that ASMD is in which state? So to hold that state, we need one variable called state reg. State register, and to update that state register we need a combinational next state logic, that is state next. So ideally state reg should be in, ideally on power up, state reg should be S0. That means in register, what is S0 value? That is 1 tick B0. So ideally FSM should be in the S0 state. And at the time of reset. And accordingly, when reset is removed, it should follow the state next. And state next, when you're not doing anything, when you're not manipulating anything, the next value is nothing but the value that is stored in the state register. And the state register, we are not driving anything, so we don't have any output. We only have the outputs like frame energy, frame valid, and ready. So we have driven frame energy, frame valid. So ready, we drive it as sign ready and press the right. So for all the outputs, we defined 3 output registers. Via 3 output registers, we have driven it to the output wires. To work internally, we require one state register. That's why what we have done, we have declared a state register. So next, what we need to do, we will go to the combinational next state logic. Here we have to define the state switching conditions, how the states need to switch. Actual logic we have to write here. So for this, I'm using a case statement, case, and here the case is inside the sensitivity list. The case we are going to look is the state reg variable, that state register. We are mainly looking at the state register. State register value is S0. State register value is S0. What it needs to do, that is begin. And if the state register value is 1, that means it is in the S1 state, what it needs to do. So these operations that I have to define over here. So I told you earlier, ideally the FSM should remain in the S0 state, and it should switch to the S1 state when start signal is logic high. So that's why what we are doing is we are monitoring the start signal. So if start, it has to do begin. Don't write the else part, I will let you know why. If start is high, what it needs to do, it has to switch it to the S1 state. So state next is equals to 1. When the FSM is in the S0 state, the ready output is logic high, since it is in the idle mode. When it is jumping to the S1 state, it is entering into the computation phase. In the computation phase, if you want to know the status of the ASM, the status should be like busy. So ready means ideal if it is 1. So in order to make the output to be busy, that means ready output should be driven with 0. So how you do that? Ready next, you make it as 1 tick B0. So on the now you made ready next to be 0. On arrival of a next clock edge, what it will do? FSM switches from S0 to S1. Why? Because state next will become state reg. Because see, state and the next state logic you are defining, right? So if you made the start signal to be high, So immediately the combinational next state logic, it will calculate like next state it has to jump to S1 state, and also ready should be equal to 0. Then on arrival of a clock edge, the FSM makes a transition into S1 state. Why? Because the combinational next state logic value is being updated into the register. So here you can see ready next is updated to 0. On arrival of the clock edge, ready reg will become 0. That means it is entered into the computation phase. And the state next is S1, right? On arrival of the clock edge, state reg will become 1. That means S1. So what it will do, so a transition has happened and ready reg is updated. When ready reg is updated, immediately ready output is driven via the register. So this is the case. If start is not coming, it will remain in the S0 state. For that, you need not write else state next equal to S0. Why? Because you have already written over here state next equal to state reg. So by default, state reg is in 0. So next state is also again 0. So it will continue to remain in the S0 state. So that is the reason we have defined here. These are the ideal conditions. And in the state switching logic, we have defined all the state switching activity. Whenever the state switching activity is not happening, or whenever any of these next state logic is not updated, it will take on top whatever the default values we have written, it will take these things. So if start is coming, then this will not come into effect. Why? Because state switching becomes activated. So if start comes, state next will be S1. So this will not become into effect. If start is 0, this entire block will not be, operations of this block will not be performed. And since there is no else part, so what it will do, whatever the state reg is there, that is will only go to state next. That means state next equal to S0 itself. On arrival of a clock edge, again the FSM remains in the S0. So if you don't want to write here, then you have to define all conditions over here. Else state next equal to 0. You have to define everything like this. So if you do like this, if you write every time like this, always it will create 2:1 marks. If you write if and else, if you do extra logic overhead will be removed. So it is always a safe side to write these conditions at the top, and in the switching activity you deal with anything, all these things. If at all, if any condition is not valid, what it will do, these will be the default conditions. So the controller will take operate on these operate on basis of these instructions. So this is the case. So once it is entering into the S1 state, what it is going to do, this begin is nothing but the ideal state. So for your understanding, I have written the description, and this is the computation. This is as per the syntax. You can write some reference names like this. After the begin, you have to give colon and you have to write. But after colon, don't give any space, and use only a single keyword for your understanding. Don't use again two keywords with a space. It will create an error. So this is the ideal state. Now what you have to do, you have to write the details of computation phase. So in the computation phase, as I mentioned, when you're jumping into the computation phase, the energy module should always scan the frame sample valid signal. So for that, if frame sample valid and so whenever this valid signal is coming, then only it has to do the operation, otherwise it should not do any operation. The first operation that we want to do is we need to do the squaring, right? So squaring means we have to do multiplication. So for doing multiplication, we need to create one another register. So that is different from this one. These are the registers and nested logic elements for the ASMD. These are declarations for ASMD. So we have register and that's a counter combinational logic part. But now we are declaring only pure register type, which is different from the register and also next state logic. It is only just a reg type. So reg, we need to declare a product. So now this product is of how many bits? So that is very important. Now we are multiplying two 16-bit numbers. So when you multiply two 16-bit numbers, the end resultant product will be the 32-bit number. So we need a rich data type of 32-bit length, that means 31 down to 0. So this prod is 31 down to 0. Now what I am doing is prod equal to what is the samples I'm receiving on this frame sample input, right? So and if you see, there are two things for a multiplier. There are two options. You can design your own multiplier, but in this I'm not designing our own multiplier. I'm directly multiplying it as a star b. Then how? Because this is not a software to do a multiplication, this is a hardware. Now who is doing this multiplication operation? How I'm getting a dedicated hardware to perform this multiplication? So if you remember, I told you earlier, modern FPGAs if you check, I told you earlier, modern FPGAs comes with a dedicated DSP blocks, which will handle arithmetic operations, mostly the multiplication. So in Xilinx, we have, I told you earlier, like in FPGA, we have basic building blocks, that is we call it as configurable logic blocks, CLBs. In addition to CLBs, now modern FPGAs have block RAM blocks, where you can configure them as RAM and ROM blocks. And then some DSP blocks are available, where you can use them to do multiplication, so on and so on. So the DSP block that is available in your Xilinx FPGA, that we call it as DSP48. What is this 48 means? It supports all operations with on operands which is having a maximum word size of 48 bits. So when I'm doing A into B, what it will do, there is a dedicated DSP block inside the FPGA, so that will be configured to perform this operation. So this what we call as DSP slice on FPGA, one resource will be used in order to do this multiplication operation. And one more important concept, we are dealing with signed numbers, right? Signed fixed point numbers, that is S F X 2.14, fractional bits 14, integer bits 2, so 2 plus 14 is equals to 16 bits. So you know that when a positive number multiplied by a positive resultant is positive, positive multiplied with negative, multiplied with positive, negative and negative is equal to positive. So anyhow we are multiplying the same number, that is frame sample into frame sample in order to square. So either we will encounter with positive into positive or negative into negative. So you need to know one more thing, how negative numbers are handled in hardware. So we use 2's complement method or way to handle negative numbers. So the multiplier, what I am talking is DSP slice. It is a inbuilt block on FPGA or inbuilt resource on FPGA that I am using it in our design. We are using this in our design. So this has a capability to operate on unsigned fixed point and signed fixed point numbers. So you have to tell to this multiplier that the operands, that is A and B, whatever I am giving, these are signed. Then only you will get a signed output. If you don't tell like that, by default the DSP slice will treat them as unsigned binary and it will give you an unsigned resultant of A plus B. But we are interested to get a means we are so the end result energy is unsigned, but however we are performing operations on signed numbers. So for that, what you have to do, you have to do the keyword called $sign . Because the inputs whatever you are giving is a signed number, so you have to intimate it as signed, and the resultant product should also be signed data, right? So it is of signed 31 down to 0 product. So that is next. We have to check one more thing. We'll try to close by 12:30 or 12:40. After that, we can take a break for lunch. So since we are calculating energy, it is we are doing x square, right? Summation of x square. But first we consider x square. So x square is nothing but x into x. So the first number is 2.14, 14 fractional bits and 2 integer bits. And second number is also 2 plus 2.14. When you do multiplication, we end up at 4.28 representation. So this is 32-bit output. This is 16-bit input, 16-bit input. Now your integer part has been scaled to 4.28. However, since your data range is from -1 to 1, and here you have taken one sign bit followed by one magnitude bit. So when after multiplication in integer part, you are getting 4 bits, right? So in this 4 bits, if you clearly observe, even the resultant, when your input is in range -1 to 1, your resultant is also in range -1 to 1. So in that case, the 0th bit, I'm only talking about the first 4 bits. First 4 bits in the sense 31 down to 31, 30, 29, 28. 28, 29, 32. 31 down to 28. Only these 4 bits I'm talking. So those 4 bits 1, 2, 3, 4. In input side, actually, we have only 2 bits, right? So one is the sign bit, other one is a magnitude bit, MB. So even after multiplication, the data range is same. It is still between -1 to 1. So your actual magnitude bit will be here, followed by the sign bit. So this is at bit position number 31, 30, 29, 28. So your actual magnitude bit will be at bit position 28 and sign bit will be at 29. So this is plus or minus. So what about this extra 30 and 31? These are nothing but after multiplication we are getting 4 bits, right, in the integer part. So that we have checked, like at the LSB side we have magnitude as well as sign bit. Now what are these extra 2 bits means? This is sign extension bit. If you clearly observe the representation, this is nothing but sign extension. So whatever this sign bit we are getting here at the 29th bit, a same copy is being copied in the bit number 30 and bit number 31. Signed extension. So again, this 4.28, what you have to do, you have to bring it down to 2.14 format. Your actual input format is 2.14, right? So when you're multiplying A into B, where A and B are between -1 to 1, then resultant, that is C, that is also in the range -1 to 1, and this resultant will be far less than A and B. If you observe, the resultant is less than A and B. So even this resultant can also be represented in the same representation of A and B, that is 2.14. But due to multiplication, we end up in 4.28 format. So what we do, this 4.28, we try to scale down and reduce to 2.14. So if you see here, our actual sign bit and magnitude bit are in bit number 29 and 28. So this 29, 28, we will take it together from as 2 bits of integer part, and remaining from 27 down to I think 14, if I'm not wrong. Just let me check. Yes, 14. So these are 14 bits. These will be the fractional part, and the bits from 13 to 0, we just truncate them and we remove. So this is called part selection. So from 4.28 resultant, we are able to extract 2.14 format. So that how we are doing is, we are extracting the data sample from bit number 29 down to 40. So this is our ultimate calculation. So that what we have to do, we have to calculate energy, right? And this value, so what we are doing, we are calculating energy equal to energy plus product. So this is previously accumulated value plus product. So the product is nothing but what we have taken just now, 29 down to 14. So 29 down to 14. Or just a minute, one minute. If you look into energy E, actually energy E we kept as 25 bit, right? So 25 bit means 11 plus 4. 11 integer part and 14 fractional part, correct? Just a minute, I'm getting. Yeah, hello. So actually I made small mistake over here. So the thing is, energy is equals to energy plus product, right? This energy is actually, we have taken 25 bit, that is split into 11 integer part and 14 fractional parts. Why? Because 11 means maximum number we can represent 1024, that is E max, maximum energy for a frame size of maximum frame size of 1024. If it is all ones, you are getting 1024, right? To represent that value, we have reserved 11 integer bits for integer part and 14 for fractional part. So but when you are performing the product, we are getting 32 bits which are represented in 4.28 format. So instead of scaling it down to 2.14 format, what I'm doing is I'm just considering all these 4 bits, and in the fractional part there are 28 bits, right? Instead of 28 bits, I'm only taking the first 14 bits. So I'm taking as 4.14, and this I'm adding it to 11.14 in the energy side. So if you're taking 11 minus 4, total 7. 7 bits shortage is there. So what I'm doing is, in order to add it perfectly, on for the second part at 4.14, here additionally we have to append 7 bits of 0. Then this also becomes 11.14 format. So for that purpose, what I'm doing is, so energy we have to calculate, that is energy next is equals to whatever the previously computed energy value that is present in the previously accumulated value that is present in the energy register, that is plus what first I have to append 7 zeros. After appending 7 zeros from the product, what I'm doing is, from 31 to 28 bits I am taking not 28, 14. But I will tell why. In this 28 bits for 31 to 28 is 4 bits, that is 28, 29, 30, 31, 4 plus 7, total 11. Up till here integer part has been completed. Now for the fractional part, what I'm doing is, again from for your understanding, I split up like this, or 70 d0 to 70 d0 comma product of part selection will be from 31 down to 14. So this is the case. I think this is understood. Even if you have not understood, I will again explain in the afternoon session how I have taken this path selection. The concept is not clear, I will explain once again, that is not an issue. But we have to complete this program, right? So I will, and like this, how many times it has to accumulate? It has to accumulate, calculate the energy value for the given frame size. So for that, how our module will know whether how many samples it has processed. So for that we need a counter register in order to count the value. So for that, what I'm declaring is a count register. The name of the count register, I will give it as sample underscore count, sample and a combinational next state value to update a counter. This is just like a counter based example that we have done yesterday. So sample count reg, sample count next. So what is the size of this counter? The size of this counter is 10 bits. Maximum frame size is 1024. To count 1024 sequences, that is ranging from 0 to 1023, we require 10 bits. So 410 is 1024, having a count range from 0 to 1023. To represent all those values, we require 10 bits. So that's why 9 down to 0, sample count red, sample count next. So when we are resetting the module, sample count red should be 10 tick d0, it should be reset. Otherwise, sample count red should be sample count next. Combinational logic, next default value should be equal to the sample. But in the computation, we have to check the counter register. That is, if sample count reg is equal to what is the frame size? How we know the frame size? The frame size is known by the frame size input. So sample count reg frame size minus 1 tick. Then what it has to do. So if this counter reaches value in the count register reaches to the frame size minus 1, that is a maximum frame size minus 1, that value, then it is an indication that it has processed all the samples with respect to a given frame size. So in that case what it has to do, it has to end the computation of frame energy and it has to go back to the S0 state. So for that what it has to do, so to go back to the next S0 state, we have to make state next equal to S0. So this is one thing, to make the state transition. And we also need to indicate that whatever the output which is available on the frame energy, now it is a valid frame energy output. So to indicate that, we have to make frame energy valid to be high. So frame energy valid underscore next should be equal to 1 tick B1. Next, once it is going to the S0 state, the module will enter into the ideal state. In ideal state, the module is doing nothing. So to represent that, ready next should be made to logic high. So that is 1 tick B1. And next, this count register should be reset to 0. Why? Because when you are calculating the energy of the next frame, the counter should be starting from the 0 to count value. So that's why beforehand we are resetting it to. So these are the 4 conditions. If this condition is not valid, there is no state transition happening. It indicates that the frame energy computation has not over. It has to be completed. So by default, it will remain in the S1 state in order to complete. And it will wait for the frame sample valid input. Whenever a frame sample valid is coming, again it will do the product. After that, it will add the resultant value to the accumulator, and again it will check whether it has processed the required number of samples or not. So here no need to write else part and no need to write remain in the S1 state. Why? Because here on the top anyhow we wrote state next equal to state reg. So whenever it is in the state S1, the state register variable will be S1 itself, and when this condition is not valid, the state transition will directly point to the same state. So it will remain in the S1 state. So whenever this machine FSM is switching to the S0 state from the S1 state, you see in the S1 state we are making frame energy value to be logic high. So when it switches to the S1 state, the logic high will be retained continuously for all the time. But as per the convention, the valid signal should be only one logic high for one clock cycle. So the moment it goes to the ideal state, then in the next clock cycle we have to make this signal to be logic low. So that's why I write one condition here. It should be logic 0. Why? Because otherwise in the ideal state it will keep on continuously pointing that frame energy is valid like that. It will be high continuously, but valid signal it should be high only for one clock cycle. That's why when it goes to S0 state, when no other frame, when the start is not initiated, or even when the start is initiated, the frame value should be 0 immediately after one clock cycle. So for to establish the condition, I have written this condition over here. Next, the else part. If see again we forgot to increment the counter, the sample count register needs to be incremented, right? Else count value is not matching with the frame size, then what we have to do? We have to increment the sample counter, because once it has processed one sample, then you need to increment the counter. And only after processing all the samples, the count value. I have not written begin and end. Why? Because there is only one condition present over here. So that's it. I think we have perfectly modeled our entire circuit. Now for this we need to write a test bench and we need to simulate it and check whether it is working as per the desired functionality or not. So I think we'll take a break and we will meet after lunch. I hope that everyone has completed up till here. If anyone has not completed, then try to complete this coding by checking the video tutorial. We will meet at 2 o'clock and we will write a test bench for this, and then we will simulate and we will check how our design module is working. So that's it from my side. If anyone has any
Thank you,
queries,
sir. We will continue after the break at 2 p.m. So in the meantime, is it possible, sir, you can share the code, a text file or anything, so that if they have any problem, they can access the code. Obviously, they will be following the video tutorial, so the link. But
yeah, I will share the text file, sir. So
yes, sir.
how do I share this
Sir,
file to
sir,
you?
you share to Mahesh, sir, and he'll put in the group.
Okay. I will send it to Mahesh, sir.
Yes, sir. Thank you, sir. We'll continue after the
Okay, sir.